Hello. So we were thwarted by technology doing this live. So I'm recording a couple videos here trying to explain the ideas of friction and how it works. We will talk about it face-to-face on Thursday. So if you have questions that aren't addressed in this video, or either some of these videos here, feel free to ask then. I'll try to answer them. You have a homework due on Friday, and friction is a big part of that. So these will be useful things. All right, let's get started. So friction is a resistive force. Sorry. Say. So it opposes motion. And unfortunately for you, it's a little more complicated than something like weight or a tension force, which, maybe you're just given a number for the tension force. Friction is more complicated in that its behavior changes depending on whether the object is still stationary or if it's sliding or whatever. And we're going to focus on dry friction. It's going to be the main thing. And we're not going to worry about the full complication. All right. So here's kind of the archetypical, simplest situation. Hopefully you can see that. Where there is an object, I don't know what this is supposed to be, an upside down bicycle helmet or something. And it's sitting on a flat surface, and there's a weight because it's on the earth. There's because it's touching the table, there's some sort of a normal force. There's some sort of a forward force pushing it forward. We call that the applied force. It means it's the force acting on the object in a certain direction. Now, in this kind of simplest case, the force is applied directly along or parallel to the surface, the table, but it could be at some weird angle, and we'll come to that at some point. Okay, we all know then from everyday experience that there's no free lunch. That's why using the hovercraft was so fun in the hallway, is that there was no friction, all right? And it was easy to make things move. In real life, in normal settings, there's some opposing force which resists motion. That thing, the word we call for that is friction. Okay. All right. So let's make some comments here. So the symbol I will use for friction is kind of a script F. It looks like our frequency symbol, but it's not frequency. Don't get them confused. And let's see, what else can I say about it? It points along the surface of contact. So when you have a flat table, then it's just going to be parallel to the table. But if you had if you had some crazy hillside or something like this, then the friction is going to, and you had a car traveling this way, then maybe let's make it simple. Let's say it's not a car. Let's assume it's a sled that looks like a box. I don't know. Anyways, if you have some object that slides along this hill, then the friction force is going to always point along the hill. So as the car, the friction force would always be along the hill. So the direction of the friction force would change with the direction of the hillside. Okay, so it always would be along the surface. And, okay, let me go back here. The amount of friction and by amount of friction, I'm being a little bit sloppy here, and I'll kind of try to be a little bit more particular. Depends upon on the surfaces which touch. Let's just say it depends on the surface. Okay, we'll get into this in a minute here, like right now. Okay, but the amount of friction somehow depends upon the details, like what kinds of surfaces you might have. Is it concrete? Is it, I don't know, aluminum? Is it steel? Is it ice? Living here in Western New York, we just had snow the other day. So those things affect the amount of friction, and I'll be more clear what's going on there. But the first thing I want you to do is to pull out the friction sampling tools that came with your textbook, which was free online. Okay, pull out your fingers. Okay, not that finger, Charles. Okay, pull out your fingers and sorry, to get away from my body here so you can see. So what I want you to imagine is if you could zoom in microscopically, get really close to two objects as they are on top of each other. So let's say this is the weird brown object in the image in front of us, and my lower hand, it represents the table. What you would see is that the objects aren't just like perfectly smooth. They all have bumps and wiggles and little crevices, and they're irregular when you get really close. So what I kind of want you to imagine is, now imagine that you were to try to hold the table, the bottom, still, and slide the object, the brown object across the top. And what you see is at first, it's kind of hard because the little pieces are interlocked. And then there's a give, and then it kind of drag, but it's easier to make things move. All right. Now, in reality, it's all very complicated, and you have to deal with all sorts of bonding and quantum effects and averaging and over surface irregularities and whatever. It's really complicated, but the basic story is right. Okay, so it's hard to make it slip, and then boom, at some point, once you get past some threshold, so you increase the force, and then I get to that place right before it's ready to go. We call that impending motion. It's almost ready to slip, and then boom, it goes. And then it's easier, right? It starts to go. There still is friction, but it tends to be less. If you've ever had to slide a couch across the carpet floor or something like that, or slide something across the floor, that it's hard to get it started. You push, and then it goes. And then, you still have to keep pushing. There's still friction there. It doesn't just move easily forever. But there tends to be less friction somehow once the object is moving. Now, what we're going to do is put all those words into a picture and then kind of wrap equations around that picture. And It's really not much deeper than that, okay? We're taking this everyday phenomenon that we all hopefully can experience, and then we are going to mathematize it, basically. All right. Now, here's here it is, right? All those words. Here's the picture. So the idea is, and here's what I shamelessly stole this from the internet. So I will put in here the lower axis. Probably got deleted or copied, cut off when I copied it. The lower axis is not down here, is it? No. Is going to be the force applied. And this should really be the magnitude of the friction force. It always opposes motion, whatever, you have to kind of think what that means, but it always is going to go in the way to try to stop or prevent motion. Okay, so what did I say with my fingers? The applied force gets bigger, and then the friction gets bigger, so as to keep the fingers from moving. So I push harder, the friction force is harder, nothing happens. Push harder, the friction force is harder, nothing happens. Okay, so that means that as you increase the applied force, the friction force increases. This is what happens before it starts to move. So this is static friction. So we have two cases. Case one is static. This is where the friction, we'll write that as F sub S for static, and it just equals the applied force. Actually, it equals minus that, but all right, whatever. It just opposes it. Okay. So if you double the applied force, so if you're here and you double it, the friction doubles. It's just 1-to-1. Easy. And then you increase, and it starts to go. Okay, so there's some sort of so the static friction, you apply more force, the static friction increases, static force increases, and then you reach impending motion or threshold of motion. But I like impending motion. It means it's ready to happen. It hasn't moved yet, but is ready to go. You're right at that threshold. Okay. And well, then something happens. It starts to go. All right. So this formula is going to change once you get past this point. Okay. So then we have impending motion. So that would be, well, think about that. That's the maximum possible static friction. So I guess it's an extra special case. Here we have impending motion. Where the static friction equals F sub S maximum. It's right here. It's right here at this point. And then what happens for almost all situations, once it starts to slide, it gets easier and the amount of friction is decreased. And it turns out, we'll go through this in Thursday, kind of in our activities, hands-on activities, that it becomes approximately constant. Now in real life, it's not necessarily so constant. It is not as nice as this graph makes it look, but yeah, all right, we'll just go with this idealized version. So at this point, we have kinetic friction. And the formula, then we'll say that the friction force we'll use is F sub K. So if it's just friction, I say F, lower, it's kind of script F. If I know that it's static, then I say F sub S. If I know that it's impending motion, I'll say F sub S max. And if I know that it's kinetic, I'll put F sub K. But if I don't know anything, I just put F. Okay, this is our narrative. This is what we experience when we think about friction in our everyday life. Okay, so remember this graph. It kind of helps. And this is what I meant when I said that friction is complicated. You kind of have these different cases and you don't always know. And what you typically will do is assume it's static friction. And then what you'll do is say something like, well, I know there's some applied force. I don't know if it's static or not. And what you really do is you do a test case and you say, well, okay, where's this peak? What is F sub S maximum? And if the applied force is bigger than that, then you know it's no good. The friction's not going to be enough to make it move. It's going to slide. On the other hand, if friction is less than that, then it might be moving or it might be stationary. So like right here, if the friction force was at this level, let me do this in, I don't know, let's choose green. Let's imagine that we knew that the friction force was at this level. Well, that could be here where it's static, or it could be here where it's kinetic, because both of them have the same height. Well, here's the thing. We are never going to ask about this situation right here. So guess what? Doesn't really matter for us. So for us, if you're less than if there's not enough friction to make it move, then you can assume that if the force applied is not enough to make it move, you can assume, you can take that back. I'm sorry. That's what happens when you change gears in the middle. You don't think through all your examples exactly. If the friction force, if the static friction is less than the maximum, if the force applied is less than the maximum amount of static friction, then you kind of have to look at the problem and you have to say, well, okay, did it start out at rest? If yes, then you're not moving enough, you're not pushing hard enough to make it start moving, so it's going to stay at rest. Otherwise, if it's moving, then you're going to just say, oh, well, the friction is kinetic because it's moving, and the applied force is whatever you're told that it is. Sorry about that. Said it in a very confusing way. Hopefully I can clarify this on face-to-face on Thursday. All right, so let's come up with some formulas then, or what can we say about this kind of situation? Can we kind of come up with mathematical formulas? What can friction depend upon? Let's go back to black. It's a little bit more clear, more visible. Question mark. So first off, this static region, before it starts to move, the friction force just equals the applied force. We've got no chance to come up with a formula for that because the friction force is caused by this applied force. That would mean I would need some sort of formula to describe your finger or whatever object is describing the push, the applied force. Well, it could be anything. And so that's going to be a really complicated thing, it depends on how your arm moves back and forth. And since it depends on a person, you'd have to somehow explain consciousness and all sorts of complicated things. So there's no way to write down a formula for this region. If it's static, all you can say is that the applied force equals a friction force. That's it. On the other hand, these other cases, it turns out we will be able to come up with formulas for. So we will be able to come up with a formula for the maximum static friction, not this red region here, can't do that, but I can come up with a formula for the maximum region, and we can come up with a formula for a flat line. So we'll be able to do that. So I can come up with formulas here for this point and this blue line, and that's it. The rest of it, you just have to look at the situation and figure it out from the free body diagram. It turns out, and I'll explain why this is a reasonable guess when we meet, that F sub S maximum equals, the magnitude of it, well, it's proportional. Some people think it should be the weight, but that can't be right, because you can, if you're out in the space station, you can still have friction. So it's not, but the weight is more or less negligible. So it's not weight that's really there. It's the normal force that should matter. So the maximum static friction, we say there's a coefficient mu sub S times the normal force. And it's the magnitude of the normal force. The normal force points up. Friction force points along the surface. They're always going to be perpendicular, so they can't just be equal. It's their magnitudes which are related. That being said, many times people will just write this as F sub S max equals mu S times the normal force. And you have to just know that you're not talking about, you're equating magnitudes, not the actual forces. What about minus signs? Well, it's static, so this is when nothing's moving. So if you apply a force, if the applied force is to the left, then the friction force will be to the right. And if the applied force is to the right, then the friction force will be to the left. They oppose each other. So there's a minus sign in there. Again, I can't tell you, I can't write that in a formula. You have to look at it and evaluate the situation. Okay, so buyer beware. All right, you just got to look at the situation and use and think about it. Where it comes out is you just draw a good free body diagram that seems reasonable, and then you put it in your force table, no problem. Okay, so that's the formula that we have for this point only. It only applies for impending motion when you're right at threshold for moving. Now, this kind of jump here, God, we're going to stay away from that. That's ugly. That's complicated. That's what causes that's what causes all sorts of things like, blackboard screech, or if you take your fingers on a surface, maybe I can do it here. Let's see. Get a little friction here. Maybe you can hear. Can you hear that? That well, it probably sounded like, but anyway, that sort of slip. So there's like a stutter. I'll do it again. Can you hear the stutter? I hope it comes through on the computer. Can you hear the stutter? That's called slip stick. Basically, it's because of moisture and stuff. My finger is kind of sticking, so it's up here, and then it slips, so it's over here, and slip stick, back and forth, back and forth, back and forth. That's that stutter sound. We won't do that. That's really complicated. All right. Now, the other case where we have a chance to model this is over here where it is just a constant. And it turns out this constant region, this kinetic friction region, F sub k, again, the magnitude of it equals, there's going to be just a constant, mu sub k times the normal force. Now, I think I jumped the gun here. These mu sub k and mu sub s, they have names. This is called the coefficient of static friction for mu sub s, and the coefficient of kinetic friction for kinetic friction for sliding. They're just numbers. What you do is you go and you offer some unsuspecting 20-year-old, 21-year-old a chance at a PhD. You say, congratulations, you're a graduate student. You lock them in a closet and you make them push things around all day and they record the results. Well, all right, maybe it's not quite that bad, but it's close. So anyway, some graduate student somewhere has gone through the terrible effort to do these experiments over and over and over and over and over and just tabulated reasonable values for these things. There's no point in memorizing them. What you can say, though, is that typically for most materials, mu sub s, the static friction, is bigger than kinetic friction. So usually, mu sub s is greater than mu sub k, usually. I'll be honest, I don't remember very many values off the top of my head, other than ice. And that's really the only ones popping into my mind. Okay. The other thing is they're all positive. They're not even really, I don't know of any upper bound. There's no reason they can't be really big. They are typically, though, less than 1. Okay. I think aluminum is like a half for mu sub s. And aluminum is considered something with lots of friction. Okay, so half. I think once you get up close to 1 for the friction coefficient, then this whole picture with fingers sliding really doesn't apply at that point. I think what we call that situation is glue. So if the coefficients get too large, you really should be modeling this as just something else. Aluminum is kind of is a funny thing. For aluminum, what I remember is there's not much of a difference between the two, and so you kind of go up and it's just a plateau. There's no drop off. And the one I remember is for ice, then mu sub s, I think, can be like, it's like 0.1 or something like 0.1 or 0.12, whereas mu sub k, I think, is like 0.08. I think it's 0.12 actually. So there's like a third of it. It's about drops by about a third as it goes from static to kinetic. So, and the only reason I know those is because every year I have to write physics problems, and so I just have these numbers in my head. Any problem you would need, you could look these up. The textbook has a table of these values. So there's no reason to memorize them. Problem will either give it to you or it'll give you everything else in the problem and ask you to solve for it. But there you go. Okay, that is what we have. So here's a little table, just putting the formulas here. They're using lowercase n, but we're going to use capital N for the normal force. And they're saying that in the static friction case, the force applied equals the static friction. At this peak, we're going to say that F sub S maximum equals mu sub S times the normal force, which is just what we had before. One last little thing. Pro tip. You never want to sound like an idiot. So this is a Greek letter mu. Okay, Greek letter mu, like it's a Greek letter M, but mu. What it is not is a large four-legged animal with horns and black spots. Okay, that eats grass. Or it's not the sound. So a cow says moo. This is the Greek letter mu. Okay, don't be a cow. Don't say moo, say mu. All right. So those are the basics of friction. I'm going to stop this video here, and then I'm going to do another example in another video here in 5 seconds. So I will go ahead and upload this to YouTube now. And if you're waiting for something to do to get ready in the homework, you can watch this. While you're watching it, I'll make the next video. All right. Hopefully catch you guys later.